By the early 1700s, scientists across Europe were becoming increasingly fascinated by electricity. They had learned how to create static electricity by rubbing materials together. They could produce sparks. They could store electrical charges in devices called Leyden jars, the earliest form of electrical storage. But one enormous mystery remained. What was lightning? For thousands of years, people had feared it. Lightning struck trees, destroyed buildings, started fires, and killed people without warning. Many believed it was a weapon of the gods. Others thought it was some mysterious force beyond human understanding. No one knew for certain. Then came a man whose curiosity would help change history. His name was Benjamin Franklin. Born in Boston in 1706, Franklin was far more than just a scientist. He was a writer, an inventor, a politician, a diplomat, and one of the most influential thinkers of his time. Unlike many scientists, Franklin had little formal education. Yet, he possessed an extraordinary ability to observe the world and ask questions that others overlooked. One question fascinated him more than most. Could lightning actually be electricity? The idea sounded unbelievable. Electricity in laboratories produced sparks. Lightning produced gigantic sparks across the sky. The similarities were difficult to ignore. Franklin suspected they were the same phenomenon, but suspicion was not enough. He needed proof. And obtaining that proof would require an extremely dangerous experiment. As Franklin developed his theory, he proposed that storm clouds contained electrical charges. If he could somehow collect electricity from a storm cloud, he might prove that lightning and electricity were connected. At first, he planned to place a metal rod on top of a tall church tower. The rod would attract electrical charges from storm clouds. However, construction delays prevented the tower from being completed in time. Franklin needed another solution. Then he had an idea, a simple idea that would become one of the most famous experiments in scientific history: a kite. In June of 1752, dark storm clouds gathered over Philadelphia. As thunder echoed through the sky, Franklin prepared his experiment. He built a kite using silk. Silk was chosen because it could withstand rain better than paper. Attached to the kite was a metal wire. At the end of the string hung a metal key. The setup was simple, but the risk was enormous. If lightning struck the kite directly, Franklin could be killed instantly. As the storm approached, Franklin and his son William launched the kite into the air. The kite climbed higher and higher. Rain began falling. The string became wet. And wet string is capable of conducting electricity. At first, nothing happened. Minutes passed. The storm intensified. Thunder roared overhead. Then Franklin noticed something remarkable. Loose fibers on the string began standing upright. It was a sign that electrical charge was building. Carefully, Franklin moved his hand toward the metal key. Suddenly, a spark jumped from the key, then another, and another. The storm cloud was transferring electrical energy through the kite system. Franklin had successfully collected electricity from the atmosphere. The result was astonishing. The electrical sparks behaved exactly like the sparks produced in laboratory experiments. The conclusion was clear. Lightning was electrical in nature. The mysterious force that illuminated storms was the same force scientists had been studying in their laboratories. The discovery transformed humanity's understanding of the natural world. For the first time, lightning could be explained scientifically. It was not magic. It was not the anger of gods. It was electricity. Franklin's experiment became famous throughout Europe and America. Scientists praised the discovery. New experiments were conducted. Research accelerated. The field of electrical science expanded rapidly. However, there is an important detail often overlooked in the popular story. Contrary to many illustrations and movies, Franklin did not allow lightning to strike the kite directly. Had that happened, he likely would have died. Several scientists who attempted similar experiments later lost their lives when lightning struck their equipment. The experiment worked because Franklin collected electrical charge from the storm cloud itself, not from a direct lightning strike. Even so, the danger was very real. Today, attempting such an experiment would be considered extremely unsafe. Yet Franklin's courage helped unlock one of nature's greatest secrets. His work did not stop there. As he continued studying electricity, Franklin introduced several ideas that are still used today. He proposed the concepts of positive and negative electrical charge. He explained how electrical charges could attract and repel one another. He developed theories that helped scientists better understand electrical behavior. Many of the terms used in modern electrical science trace their origins back to Franklin's research. But perhaps his most practical invention was the lightning rod. Once Franklin understood that lightning was electrical, he began searching for a way to protect buildings from its destructive power. His solution was elegant. Place a metal rod at the highest point of a building. Connect the rod to the ground using a conductive path. When lightning strikes, the electrical energy travels safely into the earth, rather than through the structure. The invention worked brilliantly. Buildings became safer. Fires caused by lightning decreased. Lives were saved. For the first time in history, humans were not simply observing lightning. They were controlling its effects. The lightning rod quickly spread throughout the world. Churches, government buildings, homes, and factories all began using Franklin's invention. It remains one of the most important safety devices ever created. By the late 1700s, electricity was no longer viewed as a strange curiosity. Scientists recognized it as a real force of nature worthy of serious study. Yet, a major problem remained. Electricity could be generated only in short bursts. Static electricity experiments produced sparks that lasted for mere moments. Scientists had no reliable source of continuous electrical power. Without continuous electricity, practical electrical devices remained impossible. The next great breakthrough would come from Italy, and it would change the world forever. A scientist named Alessandro Volta was about to create something humanity had never seen before, a machine capable of producing a steady flow of electricity, the world's first battery. And with that invention, the age of electrical technology would truly begin.
As centuries passed, great civilizations rose and fell. The Roman Empire expanded across Europe and eventually collapsed. Kingdoms emerged, wars were fought, empires disappeared. Yet electricity remained one of nature's greatest mysteries. Everything changed during the scientific revolution. Scientists began questioning ancient beliefs. Instead of accepting tradition, they relied on observation and experimentation. One of these scientists was William Gilbert. Born in England in 1544, Gilbert became fascinated by magnets and strange electrical effects. He spent years conducting experiments. He rubbed different materials together. He observed how objects attracted one another. He carefully recorded every result. In 1600, Gilbert published a groundbreaking book called De Magnete. The book transformed electricity from a mysterious curiosity into a legitimate field of scientific study. Gilbert introduced the term electricus, meaning like amber. For the first time, electricity had a scientific identity. Many historians now refer to William Gilbert as the father of electricity. His work inspired generations of scientists to continue exploring this mysterious force. And one of those scientists would soon conduct one of the most famous experiments in history, a simple kite, a metalke, and a thunderstorm. Long before the first human civilization appeared, electricity already existed. Lightning storms flashed across the skies. Electric fish generated powerful electrical shocks in rivers and oceans. Tiny electrical forces existed inside every atom. Electricity was always part of nature. Humans did not invent electricity. Instead, they learned how to understand it and control it. That journey began in ancient Greece. Around 600 BC, a philosopher named Thales of Miletus noticed something unusual. When he rubbed amber with animal fur, the amber began attracting small objects like dust and feathers. It seemed almost magical. Nobody understood why this happened. There was no scientific explanation, no knowledge of atoms, no understanding of electrons, only mystery. Yet this simple observation became one of the earliest recorded encounters with electrical forces. The Greek word for amber was electron. Centuries later, that word would inspire the term electricity. At the time, however, nobody realized how important this discovery would become. For nearly 2,000 years, the mystery remained unsolved. At the beginning of the 19th century, electricity was advancing rapidly. Scientists could generate electrical currents using batteries. Laboratories across Europe were filled with experiments. New discoveries appeared almost every year. Yet, one of the greatest mysteries remained unsolved. What was the connection between electricity and magnetism? For centuries, magnets had fascinated humanity. They could attract iron. They could point north. They seemed almost magical. Electricity appeared to be a completely different force. No one suspected that the two were deeply connected. Then, in 1820, a discovery changed everything. A Danish scientist named Hans Christian Ørsted noticed something extraordinary during a lecture. As electric current flowed through a wire, a nearby compass needle suddenly moved. The compass reacted as if a magnet were present. This simple observation revealed a hidden truth. Electricity could create magnetism. The scientific world was stunned. If electricity could create magnetism, perhaps magnetism could create electricity. That question would inspire one of the most important scientific investigations in history, and no one pursued it more passionately than Michael Faraday. Faraday's story was unlike that of most scientists. He was not born into wealth. He did not attend prestigious universities. He did not come from a powerful family. Born in England in 1791, Faraday grew up in poverty. His formal education was limited. As a teenager, he worked as an apprentice bookbinder. Day after day, he repaired books and bound pages together. But while working, he read the books he handled. Science books fascinated him. He devoured every page. Physics, chemistry, and electricity. The more he learned, the more determined he became. Faraday taught himself science through relentless study. Eventually, he attended public lectures by the famous chemist, Humphrey Davy. Faraday took detailed notes and later sent them to Davy. Impressed by the young man's passion and intelligence, Davy offered him a position as an assistant. It was the opportunity Faraday had dreamed of. He entered the world of professional science, and soon he would change it forever. For years, Faraday focused on one question: could magnetism generate electricity? Scientists already knew electricity could create magnetic effects, but the reverse process remained unproven. Faraday spent countless hours experimenting. Many attempts failed. Days turned into months. Months turned into years. Still, he persisted. Then, in 1831, he achieved a breakthrough. Faraday wrapped 2 coils of wire around an iron ring. When electric current flowed through one coil, he noticed a brief current appearing in the second coil. Something remarkable was happening. The changing magnetic field created by the first coil was producing electricity in the second. Faraday had discovered electromagnetic induction. It was one of the most important scientific discoveries ever made. For the first time, scientists understood how motion and magnetism could create electrical energy. Faraday continued refining his experiments. He moved magnets through coils of wire. He rotated metal discs near magnetic fields. Again and again, electricity appeared. The principle was clear. Moving magnets could generate electric current. This discovery laid the foundation for the modern world. Every major power station on Earth operates using Faraday's principle. Whether powered by coal, natural gas, nuclear energy, wind, or water, the basic process remains the same. Something turns a turbine. The turbine rotates magnets. The moving magnetic fields generate electricity. The electricity travels through power lines and into homes, businesses, and cities. The lights that illuminate the night. The computers that connect the world. The machines that power industries. All depend on Faraday's discovery. Without electromagnetic induction, there would be no large-scale electrical generation. Modern civilization would look entirely different. Faraday's work did not stop there. He also invented one of the earliest electric motors. By converting electrical energy into motion, he demonstrated that electricity could perform useful work.